In this video, we're going to discuss how we can determine the Van't Hoff factor for a specific solute. Remember that colligative properties depend on the number of particles dissolved in solution. In other words, they depend on the particles that the solute produces once they dissolve in solution. There are two different types of solutes, non-electrolytes and electrolytes. A solute that is a non-electrolyte will not break up into ions in solution. So, if one particle of a non-electrolyte is dissolved in solution, you still have one particle once it is fully dissolved. However, this differs from an electrolyte, which breaks up into ions in solution. So, for an electrolyte, you may dissolve one particle in solution. However, more than one particle results. This value depends specifically on the identity of the electrolyte and can be quantified by the Van't Hoff factor, I. I specifically is the moles of particles in the solution over the moles of formula units dissolved. For example, if we consider a strong electrolyte such as NaCl dissolved into solution, this molecule is going to break up into its counter ions of sodium and chloride, and so we have both Na plus and Cl minus in solution. Ultimately, one particle or formula unit is initially dissolved in solution, but it dissociates into 2 moles of particles in solution. So, in order to calculate I, we can consider the moles of particles in solution 2 over the moles of formula units initially dissolved, which is 1. Therefore, we calculate 2 to be our I value. Essentially, this can be simplified because you can just count the number of ions that the electrolyte dissociates into. So, let's practice a couple examples of this. If magnesium sulfate is broken up into the ions that it forms in solution, it's going to form 1 mole of the magnesium ion and 1 mole of the sulfate ion. Ultimately, magnesium sulfate dissociates into 2 different ions, so the value of I is equal to 2, just as it was for NaCl. Now let's consider the example FeCl3. When the molecule dissolves in solution, it breaks up into its ions in solution, 1 mole of Fe3 plus and 3 moles of Cl minus. We're going to have 3 moles of the chloride ion because initially we have 3 moles of chlorine in the iron 3 chloride molecule. Ultimately, we count the number of moles of ions in solution, 4, which is equivalent to the I value for this molecule. For our last example, you may recognize that C12H22O11, known as sucrose, is not an ionic compound. It is a non-electrolyte. The Van't Hoff factor for a non-electrolyte is always going to be equal to 1 because it doesn't break up into ions in solution. To elaborate, 1 mole of particles in solution over 1 mole of the formula units dissolved will always be 1. Now this table depicts how in reality we see differences between the expected Van't Hoff factor and the measured Van't Hoff factor. In other words, when we measure I, we don't see the exact theoretical values we would expect. We may expect the dissociation of an ionic compound to be complete in solution. However, the dissociation isn't necessarily complete in any given moment because some cations and anions are still paired, which may slightly reduce the value of I, such as like we see for NaCl. The importance of I directly corresponds to the colligative properties, freezing point depression, boiling point elevation, osmotic pressure, and vapor pressure, because all of these properties depend on the number of particles dissolved in solution. Whenever you are performing calculations dealing with the colligative properties of a solution, especially with an electrolyte as the solute, you must add the Van't Hoff value I to be a factor in the equation. For example, in order to determine the freezing point depression of a solution, we use the equation that delta T sub F is equal to I times molality times the freezing point depression constant. Boiling point elevation is similar in that you multiply I times molality and the boiling point elevation constant. To calculate the osmotic pressure, we must include I in the equation times the molarity times the ideal gas law constant and temperature. And finally, to calculate vapor pressure of a solution with an electrolyte solute, the vapor pressure of the solution is equivalent to the mole fraction of the solvent in solution times the vapor pressure of the pure solvent. However, Van Hoff factor plays a role when calculating the mole fraction of the solvent in the solution. Recall that the mole fraction is equal to the number of moles of solvent over the total moles of solution, so solute plus solvent. Well, when solute is an electrolyte, the number of moles of solute must be multiplied by I. Overall in this video, we have discussed the importance of the Van Hoff factor I when calculating the colligative properties of a solution with a solute that is an electrolyte.